Hi, my name is Bismarck Yeboah, a master's student in my second year of studies at the Civil and Environmental Engineering Department at the University of Vermont. I work under Professor Houston and Professor DeWalker in the Mechanical and Civil Engineering Department at the University of Vermont. I'll be presenting on our research, which is performance concrete, optimized for cost, durability, manufacturability, and sustainability. Moving on to our project statement or our research statement. So, as we already know, concrete is the most widely used construction material in the world, and approximately 14 billion metric tons of concrete was produced in 2021, as reported by the Global Carbon Project. One key material in concrete is cement that binds the aggregate together. About 4.1 billion metric tons of cement was produced worldwide, out of which 95 million metric tons was produced in the USA in 2021. This accounts for 41.2 million tons of CO2 produced, which constitutes about 5% to 8% of the world's CO2 production. In Vermont, there are several concrete producers like SDR Land, Carroll Concrete, JP Carrera and Sons, and the like. These concrete producers produce concrete to be used for several applications like transportation, pavement, and infrastructure, like the bridges and tunnels and the likes. And in order to reduce the carbon footprint in the concrete production, the amount of cement used in the concrete production needs to be optimized, and part of the cement needs to be replaced with supplementary cementitious materials like silica fume, fly ash, slag, ground glass pozzolan, which are more environmentally friendly cementitious materials. Also, in some cases, the concrete producers experience delays in obtaining approval for their concrete mixes, which can hinder the progress of their projects and escalate costs. So, this project aims to address this challenge by developing a generic concrete mix design for performance-based concrete that meets the performance specifications set by Vermont Agency of Transportation. This generic mix will be optimized to reduce costs and increase durability by employing the maximum packing density technique on locally sourced aggregates and partially replacing cement with supplementary cementitious materials. This mixed design will help reduce carbon footprint and can easily be adopted anytime a producer experiences delays in approval of their mixes. So to achieve this objective, this task will be undertaken. Yes. So optimization of the aggregate skeleton of the concrete, optimization of the binder composition of the concrete, comparison of different shrinkage mitigation strategies, and development of concrete mixes using optimized binder compositions, optimized aggregate skeleton, and the selected mitigation strategies. So when you look at figure 1 from the left to right, the first picture here shows poorly packed aggregates. And in this case, the void spaces are relatively larger as compared to the second picture. In the second picture, you can see a well-packed aggregate that has been made using packing density to reduce the void spaces, resulting in a relatively smaller volume for the cement or binder to occupy, as we can see here. Yes. The cement content of the concrete can also be partially replaced with ground glass pozzolan and fly ash, which are more environmentally friendly supplementary cementitious materials, as seen in the third and fourth picture. So moving to results. Figure 2 shows the result of packing density tests of individual fine and coarse aggregates. The packing density test was done in accordance with ASTM C29, and from the results, the sand from SD Ireland had the highest packing density of close to 0.75, followed by Galkin sand from Carroll Concrete, and also terracotta stones from Wallingford by Carrera had the highest packing density of the coarse aggregates, followed by terracotta stones from the Ireland pit by SD Ireland. Figure 3 shows the packing density of binary aggregates. That's the combination of two aggregates in a ratio of 0 to 100%. Blend B1, which is a combination of terracotta stones from SD Ireland and sand from SD Ireland, had a maximum packing density of about 0.75 at 40% fine to total aggregate ratio, followed by B4, a blend of terracotta stones from Carrera and 38 stones from SD Ireland, had a packing density of about 0.74 at 50% fine to total aggregate ratio. Packing density tests were also conducted on cementitious materials such as ordinary Portland cement, Portland limestone cement, slag, silica fume, Class F fly ash, and ground glass pozzolan. The packing density test was done in accordance with wet packing method by Kwan et al. And in this test method, it constitutes finding the maximum packing density of different binder combinations of cement at increasing water to cement ratio from 0 to 1.3. And from the test results, 75% OPC to 25% slag had the highest packing density with 60% OPC and 35% slag and 5% silica fume for a packing density of about 0.69. Tests were also conducted to determine which combinations of the cementitious materials attain higher compressive strength. Yes, so from figure 5, we can see this test. And this test was undertaken in accordance with ASTM C109, which requires making 2-inch cubes specimens of the cement mortar for the different cement combinations and crushing them on the first, third, and seventh day. So it can be seen from the test results that 75% OPC and 25% Class F fly ash and 75% PLC with 25% Class F fly ash had the maximum compressive strength of about 5,000 psi. We are also very much interested in the durability of the concrete mixes. So we run durability tests. One of them is the freeze-thaw test, which measures the resistance of the concrete specimens or the concrete to rapid freezing and thawing. And in this test method, we subject the concrete to 300 cycles of rapid temperature change from minus 18 degrees Celsius to 4 degrees Celsius, with every cycle taking about 2 hours. After every 36 cycles, we undertake the impact resonance test to measure the fundamental transverse frequency and the relative dynamic modulus of the specimens. And any specimens whose relative dynamic modulus falls below 40% is considered as failed. And fortunately for us, so far, all the mixes we've made, none of the specimens have failed yet, or have had its relative dynamic modulus fall below 40%, as seen in the figure 6. So Yes. So our ongoing works include making more concrete mixes and testing them against performance parameters and selecting the best performing mixes. We are also exploring different shrinkage mitigation strategies that works best for the concrete mixes we are making. I would like to acknowledge TIDC, Merit Foundation, and VTrans for funding this project. And we also really appreciate the material producers for this research, which include Carroll Concrete, SD Ireland, JP Carrara and Sons, and etc. And I also like to acknowledge my fellow research mate, Mr. Mohammed Abdul Kader, a master's student at the Civil Engineering Department at UVM, who have been supporting me to run the numerous lab tests. Thank you.